Well, welcome to lecture 22 in topology. The speed of this lecture is going to be, I believe the word is ludicrous. Here we go. So we tend to sell topology to non-technical audiences with homotopy. In particular, homotopy is roughly a formal method of implementing one shape flexing into another, right? So it has to do with the deformation of one shape like a donut into another like a coffee mug. So I'm going to follow Minetti, basically, and look through chapters 10 and the start of 11 in this lecture. So here's the first thing. A space is locally connected if every point has a local basis of connected neighborhoods. So connected components of locally connected space are open. In general, connected spaces may fail to be locally connected. So here's a good example of that. You have R2. You can look at the subset of R2. Right, the subset of R2, which is formed by the union of all lines through the origin with rational slope. I believe that set is dense in the plane. However, and it's also path connected, because you can pretty easily see that you can just connect the paths, connect any 2 points in this space by just running them through the origin, right? So like here, P. Q, like that. But if you take a point away from the origin, you're getting like a bunch of lines with rational slope, right? And they are very, very close to each other, but they're not touching, because you also have lines with irrational slope, and those are also dense in there. So it's path connected, and yet it does not have a local basis of connected neighborhoods, this space X. All right. Now, so that's kind of weird. So what's up next here? So let X be a topological space. And so basically the way this lecture goes is we're going to start by introducing pi 0, and then we're going to, at the very end of the lecture, introduce pi 1. All right, so pi 0 is just the equivalence. Basically, it's just you take the space and you mod by the equivalence, which says that 2 points are equivalent if there exists a path from X to Y. All right. And the equivalence classes are actually the connected components of X in this case. And we'll use this notation in this lecture. The set of paths in the space X from X to Y is denoted like so. And that just means continuous map from the closed interval from 0 to 1 to the space that begins at X and terminates at Y. So we can reflect on this in more detail. In what sense is it an equivalence relation? Well, in the following usual sense. It's reflexive, it's symmetric, it's transitive. To see reflexive, you can just take the constant path from any point to itself. To see symmetric, you look at what's called the reversal of the path. So you just take the path and do, instead of t, 1 minus t, and that goes from alpha of 1 to alpha of 0 versus like from alpha of 0 to alpha of 1. So this is the so-called reversal of the path. Right, and he introduces the notation I for path reversal operator, and that makes sense so long as your path has a domain, which is the closed interval. And in fact, he talks about a method, a strategy, in fact, to take any path and redefine its domain, as long as it's got a finite domain, to redefine that finite domain in terms of the closed interval from 0 to 1. He calls it the standard parameterization of the path. He starts with a path from A to B, and he repackages it as a path from 0 to 1. So you can do that. In fact, that's here, right here. All right, if I have a path from A to B, I can reparameterize alpha tilde, where X is alpha A and Y is alpha B, by alpha tilde of T is alpha of 1 minus TA plus TB, and that makes the parameter T run from 1 to 0, whereas the original parameter ran from, A to B. Okay, anyway, so we can also define, we can prove that the equivalence relation of paths is transitive, because you can take 2 paths, right, and you can put them together. You can do what's called join the paths, right? So we do one path and then run the other. So alpha star beta, it's a travesty to write this without drawing a picture of it, right? So basically this is the deal. Here's X, here's Y, here's Z, right? This is alpha, this maybe is beta. Alpha star beta is just running along those same set of points, but collectively. So alpha star beta is the join of the two paths. And you just play games with the parameters to make the like you speed up it, make it go double speed, and then make this other one also go double speed. So it goes through the whole parameter domain in 0 to a half, and it goes through the whole parameter domain of beta in a half to 1. So it just basically double speed the paths, and that way you can string them together with this joining. Now, the equivalence classes are path components of X, and a space is called locally path connected if any point has a local basis of path connected neighborhoods, like we talked about. For example, the balls in Rn of radius, say less than r, for t ranging between 0 and r, that gives you a local path connected basis for Rn. And proposition, suppose X is locally path connected, then the path components of X can coincide with the connected components of X. See, I think I just assume that path component and connected component's the same thing. But, you know, you can look in Mededi chapter 10, he actually has the proof of it right there, which I don't find particularly interesting, so I'm not going to cover it in detail here. So next we discuss how to transport paths via a map, all right? It's a map, it's a map, it's a map, it's a map. Well, I guess I was thinking that was Blue's Clues, but I was corrected. I guess that's Dora's Explorer, but I think the whole it's a map, it's a map, it's a map, it's a map in Dora's Explorer, it's taken on a slightly different meaning lately. Just saying. All right, let's see here. Will that get this video banned from YouTube? I don't think so. I think it's far enough into the math, no one's going to notice. Let's see here. So just I wanted to kind of visualize this equivalence class, right? So maybe you've got 1, 2, 3, 4 connected components and 2 connected components over here. You've got a mapping F that goes from space X to space Y, right? And if you take the image of a path under the function, you'll get a new path, right? And you get a new path. And, oh man, so there's some things I was going to erase. I think that was, which one was I going to erase? Well, maybe there was nothing. There's something in here I was going to erase, but I guess this wasn't it. Hopefully I'll know it when I see it. Somewhere in these slides there's an error. But, I mean, I can kind of visualize this space X mod the path equivalence is 4 dots, Y mod the path equivalence is 2 dots, and so the map F induces a map we're calling pi sub 0 of F on X mod tilde, and we're also calling this space pi sub 0 of big X. So we're using the pi sub 0, both refer to the a space of equivalence class, a space of equivalence classes of X, as well as a corresponding map induced from F on those equivalence classes. So pi 0 is being used in 2 different ways, in rather different ways, and this is a tying into his larger discussion of category theory in section 10.4, because pi 0 is actually what's called a functor. More on that in a second here. So this is how pi sub 0f it works. It takes in the equivalence class of X and it maps it to the the path equivalence of its image f of X. So anyway, oh yes, here it is. So pi 0 is a functor from the category of topological spaces to the category of sets. It sends the identity to the identity and interfaces with composition in the sense that if you take 2 maps which you can compose, then the induced maps likewise compose in the same way. So I believe that's called a covariant functor, if I remember right. And he mentions a bunch of things about category theory in that section 10.4, but I don't really have much to say about that here, let's say. Category theory is its own course. Let me try to unpack this example here. So this is an example from Mededi, which I wanted to talk about because I think it's a neat example. It's fun to try to understand it. So he has this space of, it's a compact exhaustion, an exhaustion of Rm by compact sets, right? So this is basically, it's inside the disk of radius n, and it means you're outside, you're away from the given set of points by at least 1 over n, right? So like, here's some just very heuristic pictures. I suppose I've got 3 points. I'm excluding my space x. It's x with t points deleted. So here's R2 with 3 points deleted. And here I've tried to illustrate like what would K10 look like in the green. So I'm like radius 3, and then 1/3, maybe, 1/3 out, excuse me, 1/3, let's meet 1/10 outside the points. Obviously not to scale, right? And then like K20 would be radius 20, and then you'd be 1/20th. You'd be closer to the points, but so there's definitely this nesting, like K10 is a subset of K20 and so forth. Again, don't read into the 10 and the 20 literally here. It's definitely not to scale. I'm sure if I drew it to scale, we wouldn't be able to label it or something silly, but the inclusion map is injective here, and it induces a bijection on the pi0 of K10 and to the pi0 of K20, etc. And so let me just try to talk through this here. So Minetti says some things about the complement of this exhaustion. Let me see if I feel like I might have skipped a proposition or something. No, I don't guess I did. I think this is based on that functor comment. Let's just keep processing it here. So the complement of Kn is something like everything that's not shaded over here. So if you look at that, you start to understand if I've got 3 points that are deleted from from R2, then you get these little disks around the points, and those disks are disconnected from the exterior domain. So you've got these 1, 2, 3, 4 regions, 4 connected components, and that remains the same for every one of these exhaustions, right? Doesn't matter how much you zoom in or zoom out. Well, there comes a point. You have to have it sufficiently big so that these things don't overlap, right? Like if, I don't know, maybe these are really close. If these were like a millionth apart, then you'd have to get n really big before they'd separate, But setting that kind of assumption aside, if n is much, much greater than 0, as it says up here, n much, much greater than 0, then we're in business. This is kind of the picture. And he points out that you have this inclusion map from the complement of Kn plus 1 to the complement of Kn, and that, in fact, will induce a bijection on the equivalence class of paths in these different spaces. And he points out then that, in fact, the cardinality of the equivalence class of paths is a topological invariant of X. So this is by example 10.6, which I skipped over here, didn't I? Let's see here. So 10.6, let me just talk about it momentarily. 10.6, what page is that on? 168. 168 is 10.6. And so what example 1068 shows is that you get this, if you have an exhaustion of a space by compact sets, then you can see that the cardinality of the complement of the complex sets in the exhaustion is a topological invariant of X. So in the sense that if you chose any other exhaustion of the space, you'd still get that same number of connected components, and he argues that in example 10.6. So why is this interesting? Maybe I'll explain on the next page, right? Maybe. So we can see from if we look at just the real numbers and we complement by a set S and a set T, right? And if the sets S and T they're not homeomorphic, right? If the order of the sets are not equal, right? Because then we get a different number of connected components for these sets complemented by S or T. So like that's essentially a problem in your final, right? And what example 2 in this lecture does is it generalizes that problem to Rm. See, because these exhaustions by the complement of the exhaustions of the spaces is playing the same role like the connected components did in your argument in the final, in the sense that, of course, the number of connected components is a topological invariant in the sense that if you have a homeomorphism from one space to another, you maintain the number of connected components. And in the same sense here, if we have, Rm and we delete t points from it, well, then that number, t plus 1, is a topological invariant of this. Because if you look at any exhaustion of this space by compact sets like we just did, example 10.6 says that the cardinality of the complement of the exhaustion is invariant of the exhaustion, choice of exhaustion. So if you find one exhaustion and you can calculate the number of connected components with respect to that one exhaustion, then you've done it for all. And so as such, that says other things. That says that if you take Rm and you delete a finite set T, and you take Rm and delete another finite set S, and the cardinality of S and T are different, then since that since the exhaustions are carried over by homeomorphism, if it was the case that this was homeomorphic to that, in the case that the size of S and T was different, then you get a contradiction, because you'd be able to take that exhaustion, map it over to that exhaustion. But we already know that any exhaustion already results in the same number of connected components for the complement of the exhaustion. So that's pretty neat, because that allows us to distinguish between Rm with 3 points deleted versus Rm with 4 points deleted. And we don't have to rely on our simplistic connected components argument like we did. I mean, it's still about connected components, but it's through the means of this exhaustion argument. So it's a little bit more sophisticated than what's on your final, right? But anyway, there's that. So that brings us to section 10.2, which is homotopy. So what's homotopy? Well, homotopy is that idea of deformation. And we start out like this. If you have two continuous maps, F0 and F1, from topological space X to Y, they're homotopic if there exists a continuous map F from X across the closed interval from 0 to 1 to Y, such that when we plug in 0, we get the 0th map. When we plug in 1, we get the first map. And anything in between gives you a continuous function, right? So if I fix anything between 0 and 1, like, if I fix f sub t, well, f sub t of x would be f of xt, and that's another continuous map. So I kind of visualize it like this, I've got f0 up here, and then I'm kind of continuously deforming those maps until I get to f1 down here. And so I've got this whole bunch of maps that are all together described by this, what's this called homotopy between f0 and f1. And so two functions of topological spaces are going to be called homotopic if there exists a homotopy between them, but we'll get to that. Here's just a couple of examples of homotopy before we do anything much more. So example 3, you've got a convex, there it be, I found it. Take that foul thing. Alright, so, yeah. Alright, anyway, so, sorry, I'm a dummy. Any convex set, remember convex means closed under any line segment from one point to another in the set must stay in the set, so sort of closed under line segments. Anyway, so a convex subset has, for any topological space X, if you take maps F0 and F1 from that convex space into Y, they're homotopic. Here's the homotopy. F of xt is 1 minus t f0 plus t times f1, like that. And you can try it out. If you plug in t equals to 0, then this goes to 0, that goes to 0, you're just left with f0 of x. If you plug t equals to 1, this goes to 0, and you're just left with f1 of x, right? And then in between 0 and 1, you've got a continuous, and I said from a convex set, I should say to a convex set here. Y is x is arbitrary, it could be whatever. Y is the convex set, and that's important because this addition is happening in the range of the function, which is a subset of Y, which means the context of this formula is Rn, and of course this is giving you a continuous formula. because it's just formed from scalar multiples and vector sums in Rn, which those are continuous things with respect to the standard Euclidean topology in Rn, yeah. And so like here's a picture of it. Basically you've got map f0 goes to here, f1 goes to here, and you can connect the image f0 of x to f1 of x by the line segment going from here to here, the standard, basically the standard trick that some students learned in Calc 3. Let's see, here's an example for every student should learn in Calc 3. If we have two maps f and g from a topological space X to the punctured n space, such that they're subject to this condition here. The norm of f minus g is less than the norm of f for each x in the punctured space, then you can show f and g are homotopic by pretty much the same formula as the last example, which if you rewrite it is f of x minus t times f of x minus g of x. And just to see that this mapping is, I mean, first of all, it's easy to see that if you plug in 0, you get f, and if you plug in 1, you get g. All right, that much is clear. But what happens, how do you see that this is actually into where it's supposed to go, right? How do you know that this mapping's not 0? Well, suppose it's 0. If this is 0, it means f of x is equal to that, which then means that the norm of f of x is equal to this, because we're assuming t is non-negative, between 0 and 1. And so what that gives you is that the norm of f of x is less than or equal to the norm of f of x minus g of x, which is a contradiction to the given assumption. And kind of here's a picture. So if you're like out here at f of x, right, and then you got g of x over here, well, f of x minus g of x is this displacement right here, right? And so if that is less in length than f of x, then certainly you can't get back to the origin with the blue, right? I mean, that's pretty much it. This is very much related to the geometry and, like, I want to say, oh, what's that? I think it's Roche's theorem in complex. But anyway, so there's a couple homotopies for you right there, okay? Let's go on here. Lemma. Homotopy provides an equivalence relation for the continuous maps from topological space X to topological space Y, right? And here's the proof of that. So it's pretty standard stuff. You know, first of all, prove that any function is homotopic to itself just by looking at the constant homotopy, right? F of xt equal to f of x. That's a homotopy, and that shows f is related to f. And then if you have a homotopy from f to g, you can turn it around by making the homotopy g with this formula. And like that, when you plug in 0, you get f of x comma 1, which is by assumption g of x. And when you plug in 1, you get f of x comma 0, which is by assumption f of x. So that shows you that g is related to f. So the equivalence relation is symmetric, and then you can construct, if you've got two homotopies, f equivalent to g and g equivalent to h by h and g respective. Wait a minute. By f and g respective. Come on, dude. Sorry. F. Just a second. I gotta do some work. Let's fix this guy here. All right, there we go. That kind of looks like an F. Sorry about that. So by homotopies f and g respective, then you can build homotopy h that shows that f is equivalent to h by this rule right here. And you can easily sort through that glues together nicely and gives you the desired homotopy. Now, example 5 is perhaps unexpected, but it's interesting. So if we have a map, this is a really non-trivial, in some sense, non-trivial homotopy, which is based upon a really, really neat formulation of the n-sphere. So in particular, if you have n is odd, then you can look at the n-sphere as the set of, it's a subset of R4, which can be, well, it's a subset of, not R4, but R2K, which is can be viewed as CK, and the n-sphere, we can look at it as the set of complex k vectors that have norm 1. So, and in that context, you can use the complex exponential to give a homotopy on the n-sphere with respect to that connects the antipodal map, namely f of x equals to minus x. That takes you from length 1 vector to a length 1 vector, right? It is what it says, the antipodal map. So like North Pole goes to South Pole, for example. Although we're talking about Sn, so I don't know what I mean by north and south, I guess, but I mean, maybe you do. In fact, I think earlier in Minetti, he gives a reasonably general construction of the n-sphere, an arbitrary n. But anyway, so here's the homotopy that takes you, if you plug in 0, you get the identity map. You plug in 1, you get x maps to minus x, which is the antipodal map. And this shows that for the n-sphere, the antipodal map is homotopic to the identity map. So that's interesting. And he mentions that the homotopy seen in example 5 is not possible when n is even. And so I think he basically says it's beyond the text on page 170. Although he does have some things to say about higher spheres later in chapter 11, so it's not like, I mean, I don't know how far it is beyond the text, honestly. Okay, so let's see here, page 9 of my lecture. We have next lemma. If we have continuous maps f0 g0 f1 g1 like this strung out so they can be composed, then if you have equivalence of f0 and f1, and if you have equivalence of g0 and g1, then their composites are likewise equivalent. I think the proof is straightforward, but I'm skipping it. A continuous map is homotopy. What do we mean by homotopy equivalence, right? That's the question here. It is a homotopy equivalence. What that means is that there exists a continuous map G, all right, such that f composed with G is the identity on Y, and G composed with f is the identity on X. And in this case, we say X and Y are homotopy equivalent, all right? So, like, first order of business, what if you had a homeomorphism? Would that be a homotopy equivalence? Are two spaces which are homeomorphic, are they homotopy equivalent? Well, the answer is yes. See, because if you have a function and its inverse, and that their composition is literally equal to the identity on Y or the identity on X respective, then by the reflexive property of the homotopy relation, of course, we have id Y is related to the identity on Y, and the identity X is homotopic to the identity on X, of course, which then shows you that the inverse function is a homotopy, is a quote-unquote homotopy inverse. Now, the concept of homotopy inverse is much looser than inverse function. So you can have a function which is not invertible and yet has a homotopy inverse, okay? But in any event, if two spaces are homeomorphic, then yes, they're homotopic. And the converse fails. You can have X and Y that are homotopic and yet not homeomorphic. I believe that the next example shows that. See, if we have X is a subset of Rn, and we have Y as a subset of Rm, N as in nenu nenu, M as in mommy. If these are convex subsets where N is not equal to M, and we have F and G, which are just constant maps like that, then applying the homotopy of example 3, we have that F composed with G is homotopic to the identity, and G composed with F is homotopic to the identity. Therefore, X and Y are homotopic. But they're not homeomorphic because we know spaces of different dimension are not homeomorphic from previous work. So homotopic is not the same as homeomorphic. Homeomorphic implies homotopic, but homotopic does not imply homeomorphic. But that's not bad. I mean, that's not the end of the world either, because if you can show that two spaces are not homotopic, then it does follow that they are not homeomorphic, right? So there's that. Now, lemma. If two continuous maps are homotopic, in the sense of their induced map on the equivalence class of paths, right? then what? Well, then their induced maps under pi naught are equal. And what else? What a mess on this page. Yeah. What else? And pi 0 f is bijection if f is in fact a homotopy equivalence. So there's a connection between the pi 0 that we were talking about before and now this notion of homotopy equivalence. All right. And, here's the proof of that. So pi 0 of f was x mod the path equivalence, right? And it's basically defined by this map x, path of x. The equivalence class, the class of x maps to the class of f of x, right? And likewise for g. But remember, f equivalent to g gives us a homotopy, where h of plugging in 0 gives you f, h plugging in 1 in the second spot gives you g. And notice that h allows us to form a path from f of x to g of x by let's say alpha t is equal to h of x comma t, and that means that the path of f of x, the class of f of x and the class of g of x are equal, but that says that the induced maps are equal. And if we have gamma, so if it says it's a bijection if this is true, right? So suppose this is true. Suppose you have a homotopy equivalence. Suppose gamma is the homotopy inverse. Then we know that f composed with gamma is the identity on y, and gamma composed with f is the identity on x. It not is, but I should say it's homotopic to the identities respectively, right? And then, excuse me, then we just take pi sub 0 of these relations, and we get pi 0 f composed with pi 0 gamma equal to pi 0 id. But the pi 0 of the identity is the 1 on the class of paths, and likewise over here. And then if you look at these two, what these show you is that the the induced map of the homotopy inverse is serving as the inverse map to the induced map of the function, which is to say that the function has an inverse, which is to say that it's a bijection. So there's that. And this is using the one of the lemmas I had a few pages ago about composition with pi 0. This is using the comment I wrote in red about the pi 0 being a functor. But anyway, so moving on here. A space X is contractible if it's homotopic to a point. All right, what's that mean? So homotopic to a point means that there exists a mapping f from x to p and g from p to x such that g composed with f as the identity on the space with just p, and g composed with f as the identity is homotopic to the identity on x. Notice that g composed with f of x is g of f of x. It has to be equal to p, so that means that g composed with f is a constant map, but we proved before that the constant map is homotopic to the identity map on x. All right, so, well anyway, that implies, right? Excuse me. Rather, this implies that the constant map is homotopic to the identity map on x. So this paragraph here is like half of the solution to exercise 10.6 number 1. But anyway, we can talk about contractible to a point means homotopic to a point. And he says in the definition that that's equivalent to saying that the identity map is homotopic to the constant map, right? He's basically what's underlined in green is an alternative definition for contractible. And what I've written here is half of the proof of that. But let's see here. All convex subsets of Rn are contractible following the argument that was given in example 3. Contractible, in fact, implies path connected. However, path connected does not imply contractible. The circle is a good example of that. The circle is path connected, but it is not contractible. All right, you cannot contract the circle to a point. I guess I haven't proved that, but it is true. Yeah. So let's see here. So a subspace Y of x is called a retract of x if there is a continuous map r from x to y such that r of y is equal to y for all y. So a nice example of this would be given here, and I sort of stated it more generally. If you have two spaces, right, and they just meet in a point, then if you define the r of x by x if it's an x1 and p if it's an x2, just make it constant over the second point, right? Second part of the space. Then that's going to give you a continuous function by gluing lemmas that I haven't proved, and that means then that x1 is a retract of the union of x1 and x2. Like, for example, I think in Minetti he gives this example. You got two circles, they're glued together at a point. If you define the function like I have up here, r of x, then you can look at one of the circles as a retract of both of them. So, like, kind of the idea of a retract is like shrinking things down in that way. Shrinking things down in such a way that you're not modifying the one thing, right? Like the thing you're retracting, like the retract stays put, doesn't it? It doesn't shift around, does it? Yeah. Now, a subspace y of x is called a deformation retract of x if there's a continuous map R from x cross the unit interval to x, called a deformation of x such that these conditions hold. So number one, if you plug in 0 into the second spot, you get an element of y. And if you plug in 1 into the second slot, you get that it maps back to x again. And that's for all x and x. Sorry, I seem to be losing my voice. But I will go on. We'll make it. We're going to make it. And then the second condition, r of yt equals to y for every y. So let's see here. Yeah, I don't know, my intuition's not quite where it needs to be yet to say more about it, but that's it. So like, here's an example of one. If you have a star-shaped space in Rn with star center P, you can look at this deformation retract by of that star-shaped space A by the usual. It seems like every single formula in this section. Hey, look, the formula again. It's like, look, another. Well, no, anyway. So I guess if this was a current MCU movie, this would be like a strong female lead. Let's see here, something like that. But anyway, so it's everywhere. So you can check it out and see that it works. Like if you plug in 0 into this, you just get P back, which is. So the argument is that the A is a deformation retract of of its star center. And so if I plug in 0, I just get the star center back. And if I plug in any other, y comma t here, it works out. It conspires. This formula conspires to again reduce to p. So yeah, there you go. And you can draw some pictures here. It's kind of like just it's something like just drawing everything back into the star center, right? I mean, if you, oh man, these are supposed to be lines. I tried. But, you could look at those lines and figure out how those lines relate to this formula. And yeah. All right, what else could we say? A deformation retract y, a subset of x, is a retract of x, and the inclusion is a homotopy equivalence. So a space and its retract have the same homotopy. Well, that's interesting, isn't it? So that means we can deform spaces and not change their homotopy. That's actually very interesting. Here's the proof of that, which I will skip. And here's an example, which I will not skip. So example 10 is an example of a deformation retract of the n sphere, all right? And the deleted space, Rn plus 1 with the origin deleted. And the deformation is this formula right here. R of x comma t is tx plus 1 minus t x over the norm of x. All right, so it's finally a slightly different formula, all right? So here, x over the norm of x, that's the normalization map, right? That's the hat map in my physics. Here's a picture of it. So like what's going on here is that, like I said, for fixed y, this parameterizes the line segment from like the point on the, so here this red circle here is supposed to be my heuristic for Sn, okay? And so on the n sphere, you take this point and then either you go out here to x or you go in here to x, depending on whether you're mapping to y. So maybe this should be y over, I guess this should be y over norm y to make direct correspondence with this formula, but if you can, just think about switching this to x and that to x and that to x. Anyway, the point is that, if you think about the way I was thinking about this is the deformation works like this, right? So you can take the sphere, right, and you can sort of stretch it out to infinity and smush it into zero, and like that stretching out and smushing in all together all at once is the deformation of the n sphere to the deleted space. Or of course you could think about taking the deleted space and stretching it from zero and smushing it all out to the n sphere, and then taking everything outside the n sphere and smushing it into the n sphere in that sense of the deformation, if you can imagine such a thing. But anyway, there it is. Here's the proof. These are the formulas. They don't lie. And it is in fact a deformation. So it satisfies the defining requirements. And Minetti gives some rather general and kind of cool arguments to show that, in fact, if you have a regular simplex, non-degenerate simplex x in Rn, you can deform it to its faces, right, if you want. Like, for example, you can take a triangle and you can deform the triangle to, like, these two faces. All right, so I can take this triangle and deform it to just this L. All right, so homotopy deformation, it's a pretty wild business, I would encourage you to read section 10.4 on category theory, especially if you're going to graduate school. It's something you'll hear more about. I don't have much more to say about it here at the moment. So on to path homotopy. So two paths are homotopic is a little bit stricter an idea. See, because path homotopy requires fixed endpoints. So like this fixed endpoint idea was absent in our previous homotopy idea. And so now we're looking at two paths from a given pair of endpoints, and they're homotopic if there's a continuous mapping from from I cross I to x, such that when you plug in 0 into the second part you get alpha, 1 into the second part you get beta, and then if you plug in 0 to the first part you get A, and then you plug in 1 to the first entry you get B. So I think of it like this. There is a kind of a continuous deformation of the path alpha into the path beta, and you can kind of draw a picture like this if you want. Minetti has got a nice picture that kind of is, he's got a nice orderly picture, and he's got a smushed picture like mine, whatever. Yeah, and again we can talk about this homotopy giving us an equivalence relation, and the proofs that we almost did before will pretty much transfer through nicely. So it is a genuine equivalence relation, path homotopy. And he develops a number of technical lemmas about this, right? Well, first of all, he gives an example, which is pretty nice. His nice example is that if you have a convex space, if any two paths in a convex space, well, they're homotopic. So path homotopy is kind of a little boring. Any two paths are homotopic in a convex space. So yay, there's one equivalence class. It's everything. And on the other hand, you can talk about composition and inversion of paths, and it commutes with this path equivalence. So like if you have two equivalent paths, alpha alpha prime, beta beta prime, and you join them, well then it's equivalent to the join of their equivalent paths. And likewise, the equivalence also plays nice with the reversal of paths, all right? So the reversal of path is equivalent to the reversal of its equivalent path. I shouldn't say it's equivalent. I should say the reversal of a path is path homotopic to the reversal of its to the reversal of a homotopic path. He also has this, I'll try not to get too much into this stuff because I'm not giving you all the details here, so even this is kind of a waste of your time. Sorry about that. But basically this lemma 11.3 shows you that you can take a path and you can reparameterize it according to this phi here. And if you do that, then you still have a homotopic path in that case, all right? So yeah, it's equivalent, path equivalent. Path equivalent means that it leads to the same homotopy class with respect to the path equivalence. And so we use this lemma in the next page because he bumps it up a notch here and talks about the associativity of the join with respect to the path equivalence. And so in particular, if you have three paths, alpha, beta, gamma, and you do join alpha, beta, and then you join gamma, or if you join beta and gamma, and then you join alpha, it doesn't matter in the sense that they are homotopic in terms of the path homotopy. And the proof that they're path homotopic is that you can make these two paths equal by just reparameterizing this one according to this particular reparameterization, all right? So that's kind of neat. And again, remember that this alpha join beta is just it's very simple. All you do is speed up the path on alpha and you speed up the path on beta, and you use like 0 to 1/2 in the formula for alpha and beta, and for alpha, and then 1/2 to 1 in the formula for beta, and the same thing would happen over here. So, it's straightforward but tedious to prove that this equality here is true. And since this equality here is true, and they're reparameterizations of one another, it then follows from the lemma 11.3 that they are homotopic, path homotopic. Furthermore, we have these other results about path homotopy. The constant map, like 1A and 1B are the constant paths at A and B, and so if you join the constant path to a path, you get the same as the path joined to the constant path at the end of so like at the starting point, at the ending point, it's still just the path, right? If you take a path and you join it with its reversal, you get back the constant path. What else? If you take a path and you cut it into pieces, alpha 0, alpha 1, alpha 2, alpha n, and you join those pieces together, alpha 1 joined alpha 0, join alpha 1, join alpha n, those are also homotopic to the whole path, all right? So nothing too surprising there. And also continuous maps play nice with homotopy, path homotopy, in the sense that if you have a path alpha and beta from A to B, and you have a continuous map, then the image of alpha under F is homotopic to the image of beta under F. And also, if you look at the image of the join, it's the join of the images, and the image of the reversal of the image of a path is the image of the reversal of the path. So there's that. All of these things are not terribly surprising, but they're important if you understand the details of what follows. So that brings us finally to the fundamental group. Now the fundamental group how is it defined? Well, before we were looking at paths from A to B. Now we're just going to look at loops. A loop is a path that begins and ends at the same point, all right? And if we look at the space of loops mod the homotopy equivalence, path of loop spaced at A mod the path homotopy equivalence, well, that is what's called the fundamental or the first homotopy group of X with base point A. Here, this bracket alpha is all loops that are homotopic to the given loop. And the group structure is simply defined by how do you multiply two path classes. Well, you join their representatives. And what's the inverse, the group inverse? It's to take the inverse of the path, path class represented by alpha, you take the reversal of alpha's path class. And you can prove that these are in fact well-defined operations. I have not done that, nor am I going to do that in this lecture, but you could prove it. It's involved, I believe. Well, not this so much, but there are things here that are more involved than I'm making them look. Okay, I'll just say that. So for example, if we've got a convex subspace and you take any point, well, then you can see that the fundamental group is trivial, because if you take any loop, you have a path homotopy that deforms the loop to the constant point A. And here's the proof that it works, right? So like 0 takes you to alpha, the loop. 1 takes you to just A, which is the identity map, the constant path on A, like that. And then if you look at f of 0s or f of 1f's, they're all mapping to A. So, yeah, which means that for each s in between 0 and 1, it's still a loop. All right, so here's a kind of a picture of it. You're starting at alpha and then you're deforming down to the point A. So if that's the case, if you can deform a loop to a point in your space, that means the fundamental group is trivial. All right, fundamental group is trivial. Which is to say it's the group with just one element in it, yeah? All right. So another thing you can do, which is really important, like the next step in understanding the fundamental group, and we're just going to scratch the surface in this lecture, okay? And sorry I can't go further, I ran out of time, and it's my own stupid fault for not, finding more time. It's my fault, not yours, I'm sure. Let's see here, so let me just kind of erase, I accidentally copied that down there, I shouldn't have, because I was, alright, so I think I fixed that. Anyway, so you can basically transport the fundamental group based at A to the fundamental group based at B if you've got a path that connects them. So like if gamma is the path going from here to here, and the reversal of gamma goes from there to there, right? Then this gamma sharp mapping simply takes the path, the loop at A, alpha, right? And it maps it to this. And this is a loop at B. Let me show you how. So so we start at B, and then the reversal of gamma goes over here like this, all right? And then you go through alpha, and then you go gamma back. And so what you have, what this is a path that begins and ends at B. And so what that means is that every loop at A can be repackaged as a loop at B if you've got a path connecting them. And so what that means is that the fundamental group at any 2 points in a path component will match. Thus, if x is path connected, you can define just pi1 of x to be the fundamental group, the fundamental group of the space without respect to the base point, right? If it's path connected, you can drop the base point. Now here are these calculations right here prove that gamma sharp is in fact a homomorphism of the operation, and it's also invertible. So like basically I just use the definition and then use how we defined multiplication of paths by the joining of the representatives, and then use like the path and its reversal gives you the identity map at the point, and then that like alpha times 1 is just giving you alpha, and then you like go, oh well, this is exactly gamma sharp acting on the join of alpha and beta, and so that's the homomorphism property. And likewise down here, similar calculation shows that the sharp of the reversal is the inverse function for the sharp. So that's pretty neat. So there is, again, I'm hiding stuff. There's more in Minetti. Look in there. He's got things with complicated things with 6 homotopies in order to establish the equations, which I've just rattled off as if they're obvious. They're not entirely obvious. They require work to establish. So yeah. But anyway, getting to the point here. A space is, because I wanted to make sure this lecture gives you enough information to do your final, and I think it will. So a space is simply connected if it is path connected and has trivial fundamental group. Aha, so that's what simple connected means. So like, for example, a convex subset of Rn is simply connected because it's path connected and it has trivial fundamental group. So any convex subset of Rn. So I think that pretty much solves your homework problem, because, I mean your final problem, because I'm pretty sure that you can prove that the half space is convex, right? Here's a more interesting one. The unit circle, you can find you can wind circles around the unit circle as many times as you want, right? The winding number is n here. And there's a isomorphism, in fact, from the integers to the fundamental group of the circle, which is given by n maps to this n-wound circle. And I guess Minetti later proves it's an isomorphism, but for now I'll just mention that you can prove these formulas for it, namely that, you know, the zero map maps to the identity on the fundamental group, and like the reversal of n is actually just alpha of minus n, and if you join n, if you basically, this is very, very obvious if you think about it, if you wind around in a circle n times, and then you go around another path that winds around it m times, then what you've got is n plus n winds around the circle, right? So if you understand winding number, this is totally unsurprising, but there it is. The fundamental group of the circle is not trivial, right? Corresponding to the fact that the circle is not simply connected. If you wind around the circle, you can't deform it to a point without getting off the circle, you know? And finally, one last proposition for this course this semester. The fundamental group of a product of two spaces is isomorphic to the product of the fundamental groups. So like if I've got pi 1 of the Cartesian product at the point a comma b, well, it's pi 1 of x comma a Cartesian product with pi 1. Oh, that was supposed to be a y. My bad. Although I am using, in the case x equals y, in the example which follows, so it's not too bad. My error's not too bad. See if I can make that a little sketchy. I was trying to make that into a y. I don't know if I've succeeded or not. So, stupid whiteout. Now, anyway, so the final example here, the fundamental group of S1 cross S1 then would be fundamental group of S1 cross the fundamental group of S1, which means that the fundamental group of a circle cross a circle is Z cross Z. So, I don't know, I think that's kind of interesting. And anyway, that's it. I hope this helps you guys. Thanks.